This episode of Real Engineering is brought to you by Brilliant, a problem-solving website that teaches you to think like an engineer. On the 24th of May, SpaceX launched a Falcon 9 rocket filled with 60 satellites into space. This marked the beginning of their ambitious new project called Starlink, which aims to provide high-quality broadband internet to the most isolated parts of the planet, while also providing low-latency connectivity to already well-connected cities. SpaceX aimed to make their broadband as accessible as possible, claiming that anyone will be able to connect to their network if they buy the pizza box-sized antenna, which SpaceX is developing themselves. This launch of 60 satellites was just the first of many. SpaceX has 12,000 satellites planned for launch over the next decade, dramatically increasing the total amount of spacecraft around Earth's orbit. This will cost SpaceX billions of dollars, so they must have a good reason for doing so. Let's see how this network will work and how it will compete with existing internet providers. Back in 2015, Elon announced that SpaceX had begun working on a communication satellite network, stating that there is a significant unmet demand for low-cost global broadband capabilities. Around that time, SpaceX opened a new facility in Redmond, Washington, to develop and manufacture these new communication satellites. The initial plan was to launch 2 prototype satellites into orbit by 2016 and have the initial satellite constellation up and running by 2020. But the company struggled to develop a receiver that could be easily installed by the user for a low cost. This delayed the program, and the initial prototype satellites weren't launched until 2018. After a successful launch of the 2 prototypes, Tintin A and B, which allowed SpaceX to test and refine their satellite design, SpaceX kept pretty quiet about what was next for the Starlink project, until November 2018 when SpaceX received approval from the FCC to deploy 7,500 satellites into orbit, on top of the 4,400 that were already approved. On May 24th, the first batch of production satellites were launched into orbit, and people around the world quickly started to spot the train of satellites moving across the night sky. This launch is a sign of things to come. While this initial group of satellites are not fully functional, they will be used to test things like the Earth communication systems and the Krypton thrusters, which will be used to autonomously avoid debris and deorbit the spacecraft once it has reached the end of its life cycle. Let's look at these functionalities first. We have explored how ion thrusters work in the past, which you can watch for more detail, but essentially they use electric potential to fire ions out of the spacecraft to provide propulsion. Xenon is ideally used because it has a high atomic mass, allowing it to provide more kick per atom, while being inert and having a high storage density, lending itself to long-term storage on a spacecraft. However, SpaceX opted for Krypton, as Xenon's rarity makes it a far more expensive propellant. This ion thruster will initially be used to raise the Starlink satellites from their release orbits of 440 kilometers to their final orbital height of 550 kilometers. They will also be used in conjunction with the onboard control momentum gyroscopes located here, and the US government's space debris collision prediction system to allow the satellites to adjust their orbits to dodge collisions, which we have also spoken about in more detail in a previous video. When the satellites have reached the end of their service life, they can then use the same attitude controls and thrusters to deorbit the satellite. SpaceX have included all the necessary hardware to minimize space debris risk. In their Federal Communications Commission approval application, they claim that 95% of the satellite will burn up on re-entry, with only the ion thruster internal structure and silicon carbide components standing a chance of survival. Those silicon carbide components are likely to survive as they are essential materials for the operation of lasers and thus have an extremely high melting point of 2,750 degrees. Which brings us to our communications abilities, the primary function of the satellite. SpaceX have been tight-lipped on many of the details of the satellite, but thanks to the FCC filing, we know that the satellites will contain 5 1.5 kilogram silicon carbide components, which indicates that each satellite will contain 5 individual lasers. These lasers, like our fiber optic cables here on Earth, will use light pulses to transmit information between satellites. Transmitting with light in space offers one massive advantage over transmitting with light here on Earth, however. The speed of light is not constant in every material. In fact, light travels 47% slower in glass than in a vacuum. This offers Starlink one huge advantage that will likely be its primary money maker. It provides the potential for lower latency information over long distance. In simpler terms, let's imagine this as a race between data packets. A user in London wants the new adjusted price for a stock on the Nasdaq from the New York Stock Exchange. If this information were to use a typical route, let's say through the AC2 cable, which has a return journey of about 12,800 kilometers to make through our glass fiber optic cable, in a vacuum, light travels at a speed of 299,792,458 meters per second. The speed of travel in glass depends on the refractive index, and the refractive index depends on the wavelength, but we will take the reduction as 1.47 times slower than the speed of light in a vacuum. This means the data packet will take roughly 0.063 seconds to make the round trip, and thus has a latency of 0.063 seconds, or 62.7 milliseconds. With the additional steps that add to this latency, like the conversion of light signals to electrical signals on either end of the optical cable, traffic queues, and the transfer to our final computer terminal, this total time comes out at about 76 milliseconds. Figuring out the latency for Starlink is a lot more difficult, as we have no real-world measurements to go by, but we can make some educated guesses with the help of Mark Handley, a communications professor in University College London. The first source of latency for Starlink will be during the up and downlink process, where we need to transfer our information to and from Earth. We know this will be done with phase array antennae, which are radio antennae which can control the direction of their transmission without moving parts. Instead, they use destructive and constructive interference to control the direction of the radio wave. Each satellite has a cone beam with an 81-degree range of view. With an orbit of 550 kilometers, each satellite can cover a circular area with a radius of 500 kilometers. At SpaceX's originally planned orbit, this coverage had a radius of 1,060 kilometers. Lowering the altitude of a satellite decreases the area it can cover, but also decreases the latency. This is particularly noticeable for typical communication satellites operating in geostationary orbit at an altitude of 36,000 kilometers. The time it takes data to travel up to the satellite and back down, traveling at the speed of light, is around 240 milliseconds, 369% slower than our subsea cable. However, since Starlink is intending to operate at a much lower altitude, the up and downlink theoretical latency could be as low as 3.6 milliseconds. This is why SpaceX needs so many satellites in their constellation in order to provide worldwide coverage. Each individual Starlink satellite has 4 phased array antennae located here, 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 and here. This directional beam was an essential part of SpaceX's FCC approval application, as thousands of satellites broadcasting undirected radio waves would cause significant amounts of interference with other communication methods. Once that data is received by one Starlink satellite, it can begin to transmit that information between satellites using lasers. Each time we hop from satellites, there will be a small delay as the laser light is converted to an electric signal and back again, but it is too minuscule to consider. Things get tricky here with using lasers, as we need to accurately hit the receiver on neighbouring satellites to transmit that data. Let's look at SpaceX's proposed constellation to see how this will work. SpaceX's first phase of 1,584 satellites will occupy 24 orbital planes, with 66 satellites in each plane inclined at 53 degrees. This will look something like this. Communications between neighbouring satellites in the same orbital plane is relatively simple, as these satellites will remain in relatively stable positions in relation to each other. This gives us a solid line of communication along a single orbital plane. But in many cases, a single orbital plane will not connect two locations. So we need to be able to transfer information between these planes too. This requires precise tracking, as the satellites traveling in neighboring orbital planes are traveling incredibly quickly and will come in and out of view. This means the Starlink satellite will need to switch to a new satellite in the network. This can take time. The best figure I could find is about a minute for the European Space Agency's Data Relay Satellite System, which is a currently operating geostationary internet constellation designed to serve European imaging satellites and other time-critical applications, such as serving emergency forces in remote areas like those fighting forest fires. Starlink may be faster, but it won't be instantaneous, and thus it has 5 optical communication systems on board to maintain a steady connection to 4 satellites at all times. If we now use this system transmitting from New York to London and back with the shortest path possible, using the speed of light in a vacuum as our transfer speed, we can achieve a latency as low as 43 milliseconds. Even if we took the shortest route possible with an optic fiber, which does not exist, this would take about 55 milliseconds, a 28% decrease in speed. The actual current return trip time for your average Joe is about 76 milliseconds, as we saw earlier, a 77% decrease in speed. This is a huge deal for the 2 financial markets working out of these cities. With millions of dollars being moved in fractions of a second, having a lower latency would provide a massive advantage in capitalizing on price swings. In fact, it wouldn't be the first time a communications company has made a massive investment to specifically serve these groups. The Hibernian Express cable is a privately owned optic cable that is currently the lowest latency connection between the NY4 data center in Syracuse, New Jersey and the LD4 data center in Slough, England at just 59.95 milliseconds, 39.4% slower than our best time with Starlink. The previous best time was held by the AC1 cable at 65 milliseconds. At a cost of $300 million, this 5 millisecond increase in speed was justified to just connect across the Atlantic. Imagine how much these time-sensitive industries will be willing to pay for a 17 millisecond increase in speed. It becomes even more valuable when you realize this time differential increases with increased transmission distance. New York to London is a relatively short distance. The improvements would be even more pronounced for a London to Singapore transmission. For every additional kilometer we travel, the potential gains in speed increase rapidly. But SpaceX aren't just planning on serving this super fast internet to some customers. They primarily advertise this system as a way to connect every human on this planet to the internet, and they should have plenty of bandwidth left over to serve these people. Although the internet has been one of the fastest growing technologies in human history, by the end of 2019, more than half the world's population will still be offline. Users will connect to this internet using a Starlink terminal, which will cost around $200 each. This will still be far outside the purchasing power of many third world citizens, but it's a start, and vastly cheaper than similar currently available receivers like the Chimera version at a price of $30,000. Elon Musk says that these will be flat enough to fit onto the roof of a car and other vehicles like ships and aeroplanes. This will allow Starlink to compete with traditional internet providers. It's estimated that moving the US from a 4G to a 5G wireless connection will cost around $150 billion in fiber optic cabling alone over the next 7 years. SpaceX plan to complete their entire Starlink project for as little as $10 billion. Each Starlink satellite cost around $300,000, which is already a massive cut in cost for communication satellites. SpaceX are also saving on launch costs as they are launching on their own Falcon 9 rockets, something no other satellite manufacturer has. If everything goes to plan, Starlink is estimated to generate $30 billion to $50 billion in revenue each year on the back of premium stock exchange memberships, demolishing their current annual revenue of around $3 billion. And this is a vital part of Elon Musk's long-term goals. The money generated from Starlink will mean SpaceX will have vastly more funding than NASA, which could go on to fund research and development of new rockets and the technologies needed to monetize lunar and Martian colonies. For now, the project is simply aiming to connect the world even more and potentially open avenues for education for third world countries that do not have adequate connections to the internet. Widely available internet will help solve this problem, and platforms like Brilliant have taken great steps to remedy this through their high-quality interactive math and science learning courses. Brilliant has helped thousands of users realize their potential in math and science, and it's stories like this why I am proud to promote Brilliant every month. They have a huge number of courses that will allow you to educate yourself, from foundational math courses to courses tailored for you to ace the American mathematics competition, with others geared for computer science and physics. Brilliant recently introduced a new feature called Daily Challenges, which will present you with interesting scientific and mathematical problems to test your brain every day. If I have inspired you and you want to educate yourself, then go to brilliant.org/real engineering and sign up for free. And the first 500 people to go to that link will get 20% off the annual premium subscription, so you can get full access to all their courses as well as their entire Daily Challenges archive. As always, thanks for watching, and thank you to all my Patreon supporters. If you'd like to see more from me, the links to my Instagram, Twitter, subreddit and Discord server are below.